conjecture is that this implies that V is a special subvariety, or maybe sometimes written down as a Shimura subvariety. Okay. This is the conjecture. It sort of is very clean, just classifying Shimura subvarieties by containing these points. So there's been sort of a lot of work on this conjecture in recent years. So I'll just mention a couple of partial results. So there's a theorem by Klingler, Umo, and Yafaev. They sort of came out with it in 2006, and then I think it was finally published in 2011 or so. So at some point between there, it became a theorem. Well, I don't. No, I said somewhere in the middle. I don't really know. And that the generalized Riemann hypothesis implies the Andrew-Root conjecture in general. And specifically, they needed the Riemann hypothesis for Dedekind zeta function sorry, I keep hitting this chair. Dedekind zeta functions of CM fields. So a little bit later, I'll give a brief sketch of why Riemann might be useful. But right now, let me leave it at that. And then there was a big breakthrough by, I should also mention here Edek Sokin's name. He wasn't on the sort of final paper, but he had somehow the initial idea for the whole project. And so there was a theorem by Pila in just a product of modular curves. If S equals this, then Andrew-Root is true unconditionally. So he brought in sort of a lot of new tools, and he had somehow a general program to prove Andrew-Root.
temperature at point 1 will have that behavior, the temperature at point 2 the same, the temperature at point 3 the same, etc. So what does it mean? It means in a lumped system we can determine the temperature as a function of time, but it would be bodies in which the temperature distribution inside the body is the same. There's no differentiation as a function of temperature. Examples. Good examples is a small copper ball. Small copper ball. If this is the small copper ball, and you would put it on a fire, and let's suppose the fire is at 110 degrees Celsius, then very quickly the temperature distribution inside this copper ball will be 110 degrees Celsius everywhere. There's no temperature changes inside the body. However, if you take a nice thick steak, okay, you're having a barbecue, and you've got this big piece of steak of yours, okay, and I'm going to enlarge that. So that is now the thickness of the steak. Then the temperature on the surface might be 110. But then the temperature would be 90 degrees Celsius. Then it would be 90. There it would be 40 degrees Celsius, etc. So you can see what I mean. There's differences in the temperature inside the body. But in this case, the lump system, there's no differentiation in terms of temperature. Now, paragraph 4.1 specifically addresses the lump system approach, and paragraph 4.2 further addresses all systems which are not lump system approaches. Let's look at the formulation of the mathematical formulation. The formulation is we've got a solid body, and the solid body has a certain mass, a certain volume. Okay, so I'm using that V to distinguish it later on in the module where we use V for velocity. So that is why I use that V, and this is then for volume. Certain density, and the body is at a temperature Ti everywhere inside the body. So it's uniform and it's a lumped system. So all the temperatures on the inside is the same. It has a certain surface area, AS, and on the outside we've got the heat transfer coefficient and T infinite, which is the temperature of the environment. And in this case I'm going to assume that the environment temperature is larger than the initial temperature, which means that the heat transfer will be from the outside to the inside. It can of course be the opposite, doesn't matter. So the heat transfer rate going into this body can be written in terms of Fourier's law, which you've done in the previous module. It's equal to the heat transfer coefficient multiplied by the surface area multiplied by the temperature difference, which is T infinite, minus the temperature that varies as a function of time. And what we're going to do equal to the increase in energy dt. If you find it difficult in many cases to work with heat transfer rate, think of it as a mass flow rate. So the mass flow rate going into the tank would be equal to the increase in mass of the tank if nothing goes out. Okay. Let's write that in terms of equations. It's the heat transfer coefficient multiplied by the surface area multiplied by Ts minus the temperature T over the time period dt is equal to the mass Cp dt. Terms, that one and that one. The mass is equal to the density multiplied by the volume, and dt we can write as d of t minus t infinite. Why can we do that? Because this is a constant. And if we do the differentiation of the constant, it's going to disappear. If we substitute this into those two terms, then we can write the equation as the heat transfer coefficient multiplied by the surface area multiplied by Ts minus the temperature dt is equal to rho multiplied by the volume Cpd T minus T infinite. You happy with that? Okay, so what we're now going to do is we're going to get all the temperatures on one side of the equation and the rest on the other side. So we can write it as the heat transfer coefficient multiplied by the surface area divided by rho, the volume phi, Cp, dt is equal to t minus t infinite divided by t infinite minus the temperature. Now it's almost in the form that we would like to have it so that we can integrate it. It almost looks like dx divided by x if we just change these two around. Okay? Which means that we have to put a negative sign on that side, and then we can write it as d T minus T infinite divided by T minus T infinite is equal to minus the transfer coefficient multiplied by the surface rho v Cp dt. You happy with that?
easier conjecture, or theoretically an easier.
ワンバンカーです。整理券をお取りください。整理券をお取りください。整理券をお取りください。ワンバンカーです。整理券をお取りください。整理券をお取りください。整理券をお取りください。
Special points. So if we intersect V with the CM points of S, and we take the Zariski closure, then we get V back. Then the conjecture is that this implies that V is a special subvariety, or maybe sometimes written down as a Shimura subvariety. This is the conjecture. It sort of is very clean, just classifying Shimura subvarieties by containing these points. So there's been sort of a lot of work on this conjecture in recent years. So I'll just mention a couple of partial results. So there's a theorem by Klingler, Ullmo, and Yafeev I sort of came out with it in 2006, and then I think it was finally published in 2011 or so. So at some point between there, it became a theorem. Well, I don't. No, I said somewhere in the middle. I don't really know. And that the generalized Riemann hypothesis implies the Andre-Wörth conjecture, in general. And specifically, they needed the Riemann hypothesis for Dedekind zeta functions. Sorry, I keep hitting this chair. Dedekind zeta functions of CM fields. So a little bit later, I'll give a brief sketch of why Riemann might be useful. But right now, let me leave it at that. And then there was a big breakthrough by, I should also mention here Ed Eksoven's name. He wasn't on the sort of final paper, but he had somehow the initial idea for the whole project. And so there was a theorem by Pila in 2011, which in the case where S is just a product of modular curves, if S equals this, then Andre-Wörth is true unconditionally. So he brought in sort of a lot of new tools, and he had somehow a general program to prove Andre-Wörth, which in theory could work in general, and he carried it out in this special case of x1 to the n. And so one of the ingredients that came up in his work is a conjecture which I think is of independent interest, and you can somehow conjecture. And so somehow, glibly, I'm going to call it conjecture 1 sub g. We'll see why in a moment. And what it basically says is that Galois orbits of CM points are large. Okay, so if you take a CM point, it can be defined over a low-degree number field. So there's a conjecture you can make for any Shimura variety. Let me somehow keep things relatively simple by only saying what it is for AG, which will be the subject of my talk in any case. So let AG be the Shimura variety, which is the moduli space of principally polarized abelian varieties of dimension G. And now suppose that X is a point in AG, such that if you look at the corresponding abelian variety A sub X, then this has CM type corresponding to some CM field K with some CM type phi. And I'm only going to state sort of the simplest case, which is that the degree of K over Q is 2G. Phi is a simple CM type. And in fact, the endomorphism ring of this guy is the full ring of integers of K. It's somehow the basic case that one looks at. Then the conjecture is that if you look at the Galois orbit of this point X, let me write it as the degree of the field of definition of X over Q grows at least as fast as some constant times the discriminant of K to the power of some positive number that depends only on G. Okay? So, some quantified version of saying that Galois orbits are large. In fact, you can state sort of an easier conjecture, or theoretically an easier conjecture, where you just sort of say finitely many of these are defined over Q, for example, or something like this. And in all the approaches I know, somehow, they're the same difficulty. So if you can prove anything at all, you'll probably prove something like this. At least that's what experience somehow shows. And so then it's a theorem, sort of as a result of a lot of work in the past sort of 5 years, or maybe 4 years. So it's due to Pila and myself in the case of AG. And then Klingler, Olmo, and Yafeev, together with some recent work of Christopher Daw and Martin Orr, for a general Shimura variety. And what this theorem says, I only state it in the case of AG again, because I didn't state this conjecture in general. But if you assume conjecture 1R for R less than or equal to G, then you get Andre Oort for AG. And if you assume somehow the corresponding conjecture for general Shimura varieties, then you get Andre Oort for a general Shimura variety. All right? So somehow I'm not going to say any more about Andre Oort. From now on, I'll be focused entirely on this somehow independent conjecture. So what was known sort of so far, the most sort of general version, there's been some also similar work by Olmo and Yafeev, and then I proved in my thesis that so conjecture 1G is true for G at most 6. Somehow there's some trickery you can play, and then it just stops working after a while. So today I want to announce sort of recent work with a little t, because it's still based on some work in progress, that 1G is true for all G. So as a result, you get Andre Oort for AG. So let me sort of mention that it's sort of natural, given this, to try and do the same thing for a general Shimura variety. But it seems very unclear how to generalize the approach to a general Shimura variety. So maybe it's possible, but the experts I've talked to seem to have sort of a lot of skepticism. So before I move on and just somehow talk about this problem and explain what it's really about, let me just give you a brief sketch, a very informal sketch of why this conjecture could possibly be useful to prove something like Andre Oort, why you might care. It's just like a 2-minute thing. So suppose that you have a subvariety V, say in AG, which is a, for which Andre Oort fails. Suppose you have something like this. So then V is defined over Q bar, because there's a risky closure of a bunch of Q bar points. So V is defined over some finite number field. And I'm going to cheat and say that rho log V is defined over Q, which you can sort of make happen anyways by taking a finite union of conjugates. And so then the observation is just that if X is a CM point, which is in V, then the entire Galois orbit of X is also inside V, because that's how algebraic variety works. And so the point is, if you sort of start working on Andre Oort, you might have this very, very sparse set of CM points sort of independently, and it's hard to make them work together. Whereas if you know this Galois orbit is large, then all of a sudden you have sort of a substantial amount of CM points that look very similar, and they're all in this variety. And so there's sort of a lot of approaches you can then take, starting from this fact. And in fact, that's also the approach that Yafeev took, and somehow every approach uses the somehow basic step. All right. Okay, so let me now talk about this Galois conjecture 1G. So let me sort of mention first what happens in the case of elliptic curves, and then I'll sketch what happens for CM abelian varieties. So suppose E is an elliptic curve, and the endomorphism ring of E is the full ring of integers inside some imaginary quadratic field, okay? So E is a CM elliptic curve. So then one has the following theorem. So you can call this the theorem of complex multiplication, at least one of its incarnations. And it says the following thing, that first of all, if you look at the J invariant of E, and you add it to K, then you get something which is Galois over K, which a priori is not clear. And moreover, as you go.